Okay, recording has started. So today we're going to talk about hashing. And and hashing in general, like I tried to explore as much as I can when it comes to hashing techniques. There are certain things which are going to be out of the scope of this course, and some of them are actually in the scope. So I'm going to mention all of them in general, in some detail, more or less, and hopefully it's going to be helpful for you when you are using these kind of data structures as a tool in your work. So generally, when we talk about hash table, like hashing, we are talking about them at least in algorithms and data structures. We talk about the hash tables in general. So I think it would be more appropriate to call this hash tables rather than hashing, because because hashing is actually not is actually like kind of a relatively big topic, I think, with a lot of debate and a lot of maths behind it. So without further ado, we generally use hash tables in order for us to reduce the time it needs to retrieve certain data from a data structure. So, for instance, if you have an array of data, so if you have, for example, like suppose you have something like let it be like this. So 2, 4, 1, 0, 7, 8, 6, for example, right? So suppose you have an array that looks like this, and you would like to get an element from there, right? So if you would like to get an element, one of the options that could be for you is having, for example, do a linear search, right? So this is the first technique you would actually try to employ. So you can say, okay, in order to fetch an element or an item, we check every element in the array. Okay, so this is one of the things which you would actually like do. So check every element in the array. Are you the one? Are you the one? Are you the one? Until you find the one, right? So you're like saying, okay, I'm trying to search for 7. You will go for every element in the array until you find your target. Okay, so this is the like one of the ways of finding an element in there. This is having a complexity O of n. All right, and it's O of n because this is like the worst case scenario you could ever happen, you could ever have. So it's you imagine that the element is at the end of the array, so you have to check every element until the end, right? And then you can find it. So let me just push this right here. So I'm just going to say that this is going to be O of n. Hang on, let me write this appropriately. So this is going to be O of n. Okay. Another way of doing this, right? So if you would like to minimize this a little bit more, so like you don't want to have it O of n, you would like to make it faster. One of the other ways is that you actually need to you might utilize, for example, binary search, which we're going to explore later on in this semester. So binary search, if I know how to write search. And what a binary search will have, it will have a complexity of O of log n. Okay, So this is the complexity of a binary search. And what it will do, however, you need to prepare your data structure. So in binary search, has a time complexity of this log n. It needs we need to organize our data to achieve that speed, right? To achieve the log n. If I know how to write log n. The log n speed, right? So if you would like to achieve that one, you need to prepare your data structure to become a binary tree of some sort, right? However, we would like to make this not O of log n, not O of n, but we would like to make this O of 1, right? So the moment I say, here's the data, you get it right away. No searching required, nothing of that sort. You just simply immediately jump onto that data right away. The same thing, like I think you do the same thing with dictionaries. So hash tables usually like looked at as well as a dictionary. So people use them interchangeably. I remember like I think in C sharp. So yeah, actually in C sharp, hash tables. You have a hash table data structure. However, it's not generic. The generic version of it is dictionary of T. So you have in data structure, you have in C sharp a data structure called array list, which is an automatically expanding array, right? So it's just a simple automatically expanding array. However, it receives only object as a parameter, right? However, you have the list of T, which receives a T item, right? And the list of T is the generic version. In C sharp, you have as well hash table, and it's literally named hash table, which receives as well an object type, right? The generic version of it will be dictionary of T, which is a key value pair data structure. So you have a key and you have a value, which is the same thing which is happening with hash tables. So let me erase this. I'm just simply like giving you some connections with the programming language that you are using currently in classes. So in order for us to achieve this O of 1, we really need to utilize something like the hash table. And hash tables as an ADT, or an abstract data type, or an abstract data structure, has an average search time O of 1. However, depending on the implementation, depending on the implementation, it might require hang on, I forgot how to write apparently. Require more memory. Okay. So what are the operations that we can do? First of all, you have the ability to so we can call this like supported operations. So supported operations. One is insert, which is super obvious, I think. And you insert the item itself. Two, you actually say delete, where you can actually delete the item as well, right? So you pass in the item which you would like to delete, a person, a number, a car, whatever, like whatever types you are saving in your data structure, you pass that item, not the index, nothing of that sort. However, when you search, you pass in the key, right, which we're gonna discuss in a second here. Some people actually like consider the key as the item as well. You just simply send in the item, it doesn't matter. So when we insert, so how this insertion work, right? So when we insert in an item or elements in a hash table, or into the array, basically speaking, right? Because it's at the end of the day, it's boiling down to an array. We calculate their index, because we will not insert, like, you need to actually resort to some way or some form that you can insert the element in a certain position in the array. So when you actually try to retrieve it, you know how to retrieve it immediately. You don't need to search for it. They calculate their index into that array, right? Or into that hash table, right? Actually, you know what? I can actually call this array right away because it will make more sense that way when we get to it. So it will make more sense then. Okay. So how can we actually like do that, right? How can we do this calculation? There are certain hashing techniques that you can actually utilize. So the first one is the simplest one. So let's talk about hashing techniques. So hashing techniques. So a simple hashing technique would be like, imagine that you would like to insert a bunch of numbers. So for example, we have 9, 4, 14, 7, 5, and maybe 10, right? And then you have an array. What you would like to do is that, for example, for every element you would like to insert, you could actually create an array with the maximum size of whatever the largest number you have in the array, and then you just go on from there. So you can, for example, have like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So you have an array with these indices, and what you'd say, aha, all right, so so this 9 will go right here, right? So here's the 9, right? So let me write it a little bit larger to denote it's an element. And then 4 is going to be 4, and then 14 is going to be 14 here, right? And then 7 is going to be 7, 5, and 10. Hopefully I didn't forget anybody. Okay, so when it's simple, it's similar to the counting sort, if you remember. So what we do here, we just simply create this an array with the biggest size, like with a size as big as the largest number, and then you just simply like keep inserting the elements. Now the cool part here is, when you would like to retrieve an element, you just simply say, okay, this is going to be an axis of 1, practically speaking. So you could say, for example, all right, give me an array. So this is the array or hash table, quote unquote. You say, okay, give me the element 9, right? So and it will immediately give you 9. right? It's O of 1. There is no search involved at all. You don't need to check for every element, right? However, obviously, you see the shortcoming of this is that you need to create an array as large as the largest number in the list. And if you have like two elements to insert, one of them is, let's say, 0, and the second element is 1 million, you're going to have to create an array of a size 1 million, and you're going to have an empty space of like 1 million spaces almost, or 1 million minus 2, right? And then you're going to just consume only 2 slots, and the rest is just a part of the memory which is consumed for nothing, right? So this is one of the this is the problem with that approach. So in order to avoid that problem with that approach, we actually take another approach, right? So so this is a just simple hashing technique that takes, so this, basically speaking, is taking the index is if we mathematically model it, is going to be h of x equals to x. So your hashing function is just simply takes the x, whatever number you put in, and it will just spit you out the same number, right? So that's the thing. So you, for example, say, give me the element at the index 9, and it will just simply give you 9, right? Or give me the element with that key 9 and gives you 9. These numbers, by the way, happen to be living in something which is called the key space. So they live in something which is called the key space, or keys space. You will see that in the books. All right. And this is practically your hashing function. Okay. So this is your hashing function. And right now we realize that because this is a problem, we need to make a mathematical model of some sort that allows us to index through the array and find things exactly the same way when you are searching for a word in a dictionary. You actually don't search for the word in the dictionary which you need like in a serial manner, so you don't go every page to find your word, but the words are being organized in a way that when you are trying to find the word you would like to find in a dictionary, you find it almost instantaneously, right? So it's actually, the searching is, if you are searching in a 1,000 page dictionary, or let's say usually dictionaries are measured in how many words they contain. So if you have a 100,000 word dictionary, right, you don't search through the 100,000 words, you search through, I don't know, like almost like 10 words or something like that until you find the word which you need. It's like, because how you index through the pages of the dictionary, right? So so that's that. Now, since this is actually like kind of useless, now what's going to be, how can we actually make this a little bit better? So we could, so in order to avoid allocating large memory space, we could modify the hashing function. Okay, so you just simply modify the hashing function. You don't need to allocate that much of an array, right? So how can we modify it? It's actually up to you right now. But the main thing is it has to be consistent. It has to be the same throughout the lifetime of the application, okay? So for example, I could say, okay, so the most common one, which you can find in books, is h of x equals to x modulo the size of the array. Okay. So for example, I could, let's say, allocate a 10 element array. So I could say, for example, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? So we are located right now at 10-element array. And what I can do here is I could try to insert using that function, right? Insert these numbers into this array. And when I would like to retrieve them, I will use exactly the same function, right? So I could simply say, okay, h of x equal to x modulo the size, which is going to be, for example, 9. So h of 9 is going to equal to 9 modulo the size of the array, which is 10, which is going to give me 9, right? And right now you can go on with this. So for example, say, okay, 4 is going to be 4 here, right? So 4 modulo 10 is 4. However, when you go here and you say, okay, give me 14, so if you go to H14 modulo 10, is going to give you again 4, right? And this, so 14 here, when you would like to insert 14, this is a collision. Right now, when we minimize the size of the array, we'll start to have collision overlappings, right? And there is the need, we need to resolve collisions gracefully, gracefully. Yeah, that's it. We need to resolve collisions just gracefully. We don't need to, because we would like to, we don't want to that structure just to fall apart just because of that, right? So what are the collision resolution techniques we have, right? So that's the question right now. Oh, hang on. Let me see if I can. Okay, so this is better. Okay, so let me write this down. Collision resolution techniques. All right. So what are the collision resolution techniques we have? There is open addressing. Which has a method that's a single method, which only the one which I found. Sometimes the people actually call open addressing as open hashing, by the way, just to give you the complete thing here. So in case that you are searching for something and you encounter it, you already have the name for it. Open hashing, and it's called actually chaining, right? Under that category, there's a technique called chaining. Then we have something which is called linear probing. Oh, okay. Then we have quadratic probing. And we have double hashing. Let me write this a little bit better. Then we have perfect hashing. And we have universal hashing. Okay. So these are the well-known hashing techniques that I could actually find in the books so far. So let's take one by one and let's explore them really quick. So chaining. The chaining technique is one of the simplest hashing methods. It's usually allocating a linked list when we have a collision. So simplest hashing technique where we allocate a linked list where allocate linked list at the desired array position so you're going to have basically array of linked lists. So, whoa, why are we there? So, for example, if we have a key space, of the following, so you have, for example, 8, 3, 13, 6, 4, and 10. Okay. So what we can do is saying, okay, so we're going to have 0, 1, or let me just write it without the commas. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, and your hashing function is going to be h of x equals to x modulo the size of the array. Okay, so assuming that this is your hashing function. And then what you're going to do here is you're going to say, okay, let me insert the 8. So you will find, you will actually say 8 modulo the size. So 8 modulo 10 is going to be 8. And then you go to the index 8, right? And then you fetch the element, right? But instead of fetching it, of course, you insert it. But so we're going to actually create a linked list. And we're going to put 8 here. So we're going to have a linked list. Right now we are pointing. So that thing is pointing to, well, let me write it. There are many annotations to write to draw a linked list, actually. So let me draw it a little bit better. So this is going to be 8, right? And this should be pointing somewhere, right? So either pointing to null or just simply draw it in that way. The next element will be 3. So you actually say 3 modulo the size, which is 3 modulo 10 is going to be 3. We create a linked list. We put 3 here, and it doesn't point to anywhere. And then we get 13. 13 is also going to be 3. So 13 modulo 10 is going to be 3. So right now, I'm going to actually go to the index 3 and add one more element to the linked list, right? So right now, we have 3 and 13 here. So 6 is going to be exactly the same thing. So 6 is also pointing to nothing. Oh, come on. There we go. 4 is going to be exactly the same story. And 10 is going to be at 0, so it's going to be right here. Okay. So this is the so this is how we can be actually inserting using chaining method. So what we do here is like we say, okay, I would like to retrieve, let's say 4, right? So you say, okay, h of x, so h of 4 is going to be 4 modulo 10, which is going to be giving me 4 again. I will go here and fetch the element from the linked list, right? Which is going to return to me 4, okay? Now, comes the question here is I would like to grab 13 right now. So you're going to say, okay, 13 modulo the size, which is going to be 10. So 13 modulo 10 is 3. You will go here, you will say, okay, give me the first element. So the first element is 3. It is not 13, so it's not my element. You just simply skip that and you go to the next element, right? The next element is 13, so this is mine. I'll retrieve it, right? Now, obviously, it is not O of 1, but on average, it's O of 1, all right? However, the problem with this one is you need to maintain a quite interesting data structure, like kind of layout and memory allocations. It actually can get kind of slow. That's one thing. And the second thing here is the worst case scenario that could ever happen to you is having, like, for example, having a collision of that sort. Imagine that you are inserting 20, 30, 40, 60, 10, right? So imagine that you are inserting something like this. The modulo, if you use this formula, so x modulo the size, you would actually end up with all the time index 0. So you will end up, for example, with an array, let's say of 10, that all the indices are actually lined up. So all the elements are lined up at that point, right? At the index 0. And you have a huge linked list of numbers. And whenever you are trying to retrieve an element, right now it becomes O of n. You are searching every element in the list until you get your element. So if you, let's say, for example, give me, so you insert all of these stuff, and it's all things are nice and dandy. And then you say, give me 60, and 60 right at the end, right? You will actually say, so h of x is going to be equals to 60. So h of 60, practically speaking, modulo 10, right, is going to give you 0. So you say, okay, I'm at index 0. So you're going to go say, hi, are you this one? So this one is 10, 20, 30, yada, yada, until 60, right? You will keep checking each one of those until you reach to this one, which is almost like, which is exactly the same as a linear search, right? So this method has a little bit of a shortcoming, right? So so we need a little bit of a better approach, right? So that's the point of the story here. So this is chaining, practically speaking. The next one is, so a better way of, might be a better way of doing this, like let's enhance it a little bit. We use something which is called linear probing. Okay, so use linear probing. So what linear probing does is it's quite actually it's actually quite simple. It actually, like, it has a little bit of a different way of, like, that it's not h of x equal to x modulo the size. Probably at the insertion time it is, but it's a little, but again, it's a little bit different. So let me show you what I'm talking about here. So imagine that we get the same example as above, so or as below. Let's actually give us, let's get another one. So I will just simply write in 9, 4, 14, 7, 5, and 10, right? So imagine that you have these that key space, and you would like to insert that into the hash table, okay? So what it does exactly is you have let's say we have a 10 element array, so 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, okay? So imagine that you have an array allocated, so you have 10 element array allocated in the memory, and you'll say, all right, so I would like to insert those guys. So what you will do, you say, okay, let's use the same functions as before. So you say h of x equal to x modulo the size. Right? So you say, okay, let's insert 9. 9 will go here because 9 modulo 10 is 9. Okay, let me write it in a different color to be obvious. And then you say, okay, let's insert 4. 4 will go here. So no, we will not allocate any linked list if you haven't noticed yet. Now 14, so 14 modulo the size, which is 10. So 14 modulo 10 is going to be 4 again. 4 is already occupied. We go to the next element. And if the next element is actually empty, or the next slot is empty in the array, we just simply insert it in there. Coming up next, 7. So 7 is going to be here. 5 is going to be, so 5 actually, so 5 modulo 10 is 5. 5 is already occupied. So you will insert, so you will actually go to the next empty element, and the next empty element has to be, happen to be 3. So you put 5. And then 10, which is going to be 10 modulo 10 is going to be 0, which is going to be here. Does this make any sense?
Yes, it does.
Yes, it does.
All right, perfect. So this is what linear probing is about, right? You just simply try to find the next slot. Now, I just lied to you about this formula. The formula doesn't look exactly like this. Actually, the formula looks like this. So h of x equals to h of x plus f of I modulo the size, actually, where f of I, so f of I is a function that returns to you 0, 1, 2, 3, and so on and so forth. Okay? So this is what f of I is. It's just a function that returns to you a single number, a normal, like an integer number from 0 up to n. Okay? So if you are, for example, having a collision, or actually if you are inserting a number, this I is going to be always 0. Okay? Whenever you are trying to insert, it's going to be always 0. So h of x, so h of 4 is going to equal to, and we know that it's actually modulo x modulo the size, by the way. So it's going to be h of 4 plus, so this is, let's call it h hat, so, or h dash, f of 0, right, modulo 10, okay? So this will give me 4, right? So 4 plus 0, because this function returns to me the number which I put in, so it returns to me I, so f of I is practically I, okay? So 0, it will return to me I, so it's going to be 0. Modulo 10 is going to be 14. Now, if I actually give it, sorry, it's going to be 4, sorry. If I actually give it 14 right now, so h of 14 plus f of 0 modulo 10 is going to give me again 4, right, which is a collision. So what we do, we increment that I. So we say, okay, h of 1, 14 is going to be h of 14 plus f of 1, right, modulo 10. So this is going to be 4, right? So h of, sorry, it shouldn't be, like, I shouldn't actually, like, I should have, yeah. So 14 plus 1 is going to be 15. 15 modulo 10 is going to be 5, right? And this is why we have 14 at the index 5, right? So this is how the function will look like. So this is the collision resolution when it comes to linear probing. Makes any sense?
Yeah, it does.
All right.
Yes, but I have a question.
Hit me with that question.
What if if everything is occupied?
You don't have a space. That's it. The hash table is full. Okay. So
Makes
you have
sense.
to be, yeah. So yeah. When you allocate the, if you can actually have an automatically expanding hash table if you want to, but right now you have to code it for that. So probably you need to recalculate the indices again. I think. So recalculate, like when you're reinserting back things, you need to recalculate how things will be inserted back. All right, so now it goes, by the way, just for you guys, like if we think about this, like, so for you right now, it actually will start to get easier and easier. Because right now the quadratic, so we have this quadratic probing. So quadratic, let me write it, let me be consistent a bit. So,
Imam ja, profesore, pitanje.
pitaj.
F od I, to je zapravo ovo mjesto u nizu, je li tako? I sad, ako smo ga već zauzeli sa četvorkom, mi to mjesto u nizu povećavamo za 1, je li tako?
Aha.
Dobro, hvala.
Ništa. So quadratic probing. Actually, this is like, if you look at this, you can think of it like this is the I inside your for loop, right? For int I equals to 0 and I plus plus, whatever, I less than the size and I plus plus. This is actually the one which you are incrementing, practically speaking. Now, the quadratic probing, actually, what it does, it resolves one problem of the linear probing, which is clustering problem, right? When you have a little bit larger array than this, okay, what would happen is that you might end up with, if I look at the layout of the array in the memory, right? If this is a very large chunk of the array, you would actually find that you have clustering in the memory because of the linear probing. And the clustering will happen right now. We cannot see it here because the array is actually quite small. I mean, you can see it relatively here, like you have this part and then you have this part and this part, right? But when the array gets a little bit bigger, with linear probing, you always seek the next closest element after a collision, right? So you say, okay, we have a collision, just give me the next one, right? And then if you have similar, like closer indices results, if you get results that are closer to each other when it comes to indexing inside this data structure, you might actually end up with clustering quite easily. And then you get like fragmentation in the memory. So in order to avoid that, people actually have said, okay, let's, instead of having just a hashing function that looks like so, the collision resolution would be as simple as, so it's going to be the same as linear probing or similar. Let it be like this, similar to. I think similar writes with double L, I think. Similar to linear probing, but has a different hashing function, or slightly different hashing function. Oh boy. To avoid clustering. Okay? And the hashing function is exactly identical to this. So h of x, so h hat of x. When it comes to collision, we use this h of x plus f of I modulo the size, right? However, f of I is going to return to me I squared. All right. So do not return to me the same I, just simply square it. So in terms of the collision, you will end up with, for example, if you keep incrementing 1, so when you increment this 1 to 2, let's say, in terms of when a collision happens, so it's going to be 2 to the power of 2 is going to be 4. So 4 plus 14, right? So just to be clear here, modulo the size. Okay. So this is the trick. It just what it will do, this kind of trick, what it will do, it will relax this a bit. It will relax it. So it will just make this clustering a little bit more spread. So you don't have large fragments of memory, like large fragmentation in your memory. Okay? That is what quadratic probing is all about. Just minimize just minimize this clustering problem. All right, so the next one, which is going to be double hashing. So it is actually similar to, again, linear and quadratic. However, we actually like use a different hashing function. Like we hash the thing twice actually, in order for us to make sure that we don't have a problem with collisions, let's say. So similar to quadratic and linear probing. Except it relies on two hashing functions. Hang on. Two hashing functions. It's kind of crazy glitching here. Instead of one, okay? So if this is going to be the first hashing function, equals to x modulo size, okay? The second one will be whoa. Will be h2 of x is going to be actually m minus x modulo m, where m is the closest prime number to the size of the array. All right. So usually your final hash would look something like this. So the final hashing function will look like this: h of 1x plus j h of 2x times h of 2x. So h2 of x. So h1 is this one, h2 is this one. Okay. Where j is just an increment when you have a collision. So j where, so let me write this a little bit better. Final. And j is just simply 1, 2, 3, 4, 5, and so on and so forth. Okay. Now a prime number, for those who I forgot the name of it in Bosnian, to be honest. The prime numbers are the numbers which can be only divisible by one in themselves, I think, as far as I remember. So if you have, for example, like an array of size 11, let's say the closest prime number will be 7. Prosti broj, exactly, thank you. So it's going to be the closest one is going to be 7, let's say. And this is practically it. Nothing more to it. This is how to have like this is what double hashing is all about. What it does is it actually minimizes the collision as much as possible. This formula, I actually picked it up from the art. Oh boy. Okay, from the art of computer programming book. It's a very famous book, and it's quite academic. I mean, it's not quite academic. It's actually quite good. Very, very good book. Let me just try to correct this thing. So it's very, very good book. And it's like a series. I think there are like four volumes, 4.5 volumes. Go ahead and check it out. It's actually quite a relatively large book, but it's actually quite good. It covers a lot of interesting topics about computer science in general and algorithms and everything else. So yeah. Moving on. Is this actually clear to you guys? Are there any questions regarding this bit?
Everything is fine.
All right, perfect. I think it's actually like kind of relatively easy right now. Things are a little bit like all of them are similar, just simply an improvement over every technique, just so you have a slight improvement above it. Now let's go to perfect hashing. And perfect hashing is a little bit different. Perfect hashing, what you have here is like the simplest way to put it is it's a hash table of a hash table. So so it's a good for searching in general, but not that good for when it comes to insertion or deletion, because when things gets resized, it gets a little bit slow. But searching is actually quite good. Has a similar idea or implementation. It has similar concept to chaining. Except instead of using linked lists, it uses hash tables, or it uses the same technique, hash tables. And what will happen is you're going to use, for example, an h1 of x, for example, for the initial hashing, for the initial position in the array. So you're going to have a hashing function to find position in the array. The second hashing function will actually find the position in the subarray, right? Okay. All right, so if you have, for example, something like an array like this, you have a normal hash, like a normal, yeah, let me just put it like a little bit normal. So if you have a hash table like this, and you found your index using h1, for example, that happened to be inserting like the 0, 1, 2, so you are trying to insert 20, what will happen is you will have to allocate another one where you're going to actually use h2 to insert inside that array, right? So you'll insert, let's say, 20 here. Yes, you will consume more memory, but on average, you're going to have a super fast searching time. Okay? And this is what perfect hashing is all about. Touchdown. Easy. There's nothing more fancy, I think, about it. I mean, there's obviously, by the way, I'm actually like, I'm skimming a lot of details here, but you guys need to research and read more about it in the books. I'm just giving you like the basic ideas of what's happening in there. The final one, and well, then I'll let you go. The final one would be the universal hashing. Now, according to what I've seen in the books, in the book rather, whoa, I written universal twice. What the hell? Hashing.
I have a question.
Yeah.
About the perfect hash.
Mm-hmm.
So it's similar to the one where we use the linked lists, but this time the second hashing function is just gonna immediately find the index.
Yes.
Right? Oh.
Yes, yes.
Okay.
All right, so universal hashing. Now, universal hashing is, it doesn't actually require you that you find that you like it doesn't require you to allocate more memory, like more lists or something like that. But what it does in universal hashing is it uses a little bit more interesting concept. Usually, like I think in the MIT book, which I've given you, the Introduction to Algorithms, 3rd or 4th edition, depending on which edition did you pick, they mentioned universal hashing in the way, and they are the only one apparently for some reason. I couldn't find it in the Art of Programming or in the one which is data structures and algorithm analysis in C. I didn't find it there. They mentioned that they were talking about like the security aspect of it. So what you happen to have is you don't have one hashing function, you have several of them. So you have something which is called the universe of hashing functions, right? It's a collection of hashing functions. And what you do is you choose one of them randomly at a runtime. And then once you choose one, you stick with it until the end. So for example, if you use, let's say, hashing function 1 randomly, or a hashing function number 6, let's say, you pick up that hashing function and you keep working with it throughout the lifetime of the application. Once you exit the application, it's done, everything is destroyed, right? The memory is cleared out. And when you boot up the application again, you will not use again 6, you will use, for example, number 4 or 3, because you are picking things at random. And hence the adversary, or people who are trying to hack into your system and trying to figure out what's happening into your memory, they cannot figure out the hashing function based on your patterns of usage. So you are using, each time you are using a different hashing function, so nobody can figure out which hashing function you are using unless they get the whole like dictionary or the whole universe of hashing functions which you already have. Okay. Not only that, they were talking, also the book was talking about like how the universal hashing is also having this algorithm within it to filter the bad hashing functions. Now, I will not actually discuss about this more. I just wanted to give you, to tell you that this thing actually exists. So let me write this down just to make this class complete. It relies on having a collection of hashing functions that we pick at random and we stick with it throughout. Actually, throughout is written together, I think. The runtime of the application or of the program. Okay. So how it's actually being done? Like what is actually the formula of that thing? So we begin choosing by a very large prime number p. So 1, choose a very large prime number p. Okay. And you have another number, so you have like this one, so 2. We have b, which belongs to 1, 0, 1, ranges from 0, 1 to until p minus 1. All right, so it doesn't exceed p. And you have another one, a, belongs to. This time doesn't start from 0, it starts from 1, 2, 3, and so on and so forth until p minus 1 as well. Okay, so you choose this p, and then you define, b and a, which are ranging, so b ranging from 0 until p minus 1, and a ranging from 1 until p minus 1. Okay, and m is the size of the array. Your hashing function, HAB, of a given key is going to equal to, or so k or x is the same. Let me put it x since I used x all the time. A of x, so a times x, plus b, modulo p, mod m. This is the actual hashing function. And what we do, we choose these guys at random. Okay? So you start shuffling these A and Bs, and that's pretty much it. Okay? So this is, by the way, universal hashing. There are lectures. You can find it online. It takes like an hour or so to describe. It's actually like, it's not, I just compressed the information a bit. I advise you actually to look into it. A lot of people talking about security when it comes to this, especially the book or the books. So give it a look. So yeah, and you're going to be using dictionaries, I think, throughout your career in development. So it's good to know how these things actually work. If you are keen to know about this in C#, you have dictionary of tk, where t is the key and k is the value. Okay, so this is the name of the collection in C#. So go ahead and check out MSDN for that, for more complete information. Any further questions for me here? Is all clear here?
Yeah, it is.
It's all good.
All right. I will stop recording.